Hello everyone. In last class we discussed about classification of problems into P and NP class. We have seen what is the P class problem and NP class problem. As we discussed in the previous session that the problems which are solvable in a polynomial time are considered as P class problems, and for these problems there exists a deterministic polynomial time algorithms. Okay, so if these properties are satisfied, then these problems will be considered as P class problems. Okay, and next one we have also seen some of the problems will be considered as NP class problems if these problems are not solvable in a polynomial time. And for these particular problems we have something like non-deterministic polynomial time algorithms. And moreover, for these problems, if there exists a solution, that solutions can be verified in a polynomial time. Okay, and we have seen the some of the examples that are related to P class problems and NP class problems. So as we know that the problems for which there exists deterministic polynomial time algorithms, those are called as P class. The examples are binary search, linear search, sorting, minimum spanning tree, etc. Whereas the NP class problems examples are traveling salesman problem, graph coloring problem, satisfiability, etc. So these are the various classification of problems into two categories. After this, we considered a diagram in which we represented that P is a subset of NP. Okay, so whatever the problems which are deterministic, which are non-deterministic today, they will become a polynomial time algorithms in the future days. Okay, so we could say that the class of P will goes on increasing as more number of non-deterministic problems will get solvable in a polynomial time. Okay, and next one we are having the another class of problem which is called NP complete and also NP hard. So there is a relationship between these two categories. So first thing, let me discuss about the NP hard problem. So here, a problem that belongs to NP class is reducible to NP hard. Okay. So generally, what I mean to say is that if you get an algorithm for a NP hard problem, that algorithm can be used to solve the problem which is there in NP. Okay. So if this property is satisfied, then we could say the problem is NP hard. Okay. And next one, we could also define this NP hard problem by considering the NP complete property. So here you could see the definition. A problem P is NP hard if there is an NP complete problem Q. So here we are considering that P is a NP hard problem, and we are having a NP complete problem Q. So if problem Q is reducible to P in a polynomial time, then we could say that P is a NP hard problem. Okay. So here the meaning is that if you are having an algorithm for NP hard problem, that algorithm can be used for solving the problem that is there in NP class. Okay. Then next one, we are having the another definition, that is NP complete. Okay, so for NP hard problem, if you are having a non-deterministic polynomial time algorithm, and if that problem is NP hard, then it becomes a NP complete problem. Okay, so here to say a particular problem is NP complete, it must satisfy the two properties. The first one is that it must be NP hard, and next one, it belongs to NP class. Okay, but here in case of NP hard, a problem could not be a NP class, so could not be from the NP class, right? So any harder problem can be considered as a NP hard problem. Okay, if that problem is NP hard, and if you get an algorithm, non-deterministic algorithm that gives solution in a polynomial time, then that NP hard problem will become a NP complete. Okay, so this is a difference between the NP hard and NP complete. Next one, here we are going to see that how to prove a problem is NP hard, and how we apply the concept of reducibility for checking or proving the problem is NP hard. So first thing, I am considering the base problem which is considered as a NP hard. So here the problem is CNF satisfiability. So this is something like Boolean circuit satisfiability problem. Okay. So just try to understand this problem. So here we are having the three Boolean variables x1, x2 and x3 which is represented as set of x1 comma x2 comma x3 and I am denoting is with xi. Okay. So I am having set of three Boolean variables x1 comma x2 comma x3 and I am denoting it with xi. Okay. And next one here it is a satisfiability problem. So CNF is equal to. So here I am writing one formulae or satisfiability equation. So like x1 uh, or x2 bar or x3 that is perform AND operation with x1 bar or x2 or x3 bar. Okay. So what we have to do here is we have to find the values of x1, x2 and x3 such that the result of this equation will become a true. Okay. So we have to find the values of x1, x2, x3 such that this satisfiability equation gives the true result. Okay, or it gives the value as 1. So to find out the solution for this problem we have to generate all the possible combinations of x1, x2, x3. So if we consider the combination x1, x2, x3, so we are going to get around 2 power 3 combination. So that means we are going to get around 8 possible combination, right? So among these 8 possible combinations, we have to find out one combination by using which we will get the result as true for this satisfiability equation. Okay. So by seeing these particular combinations, we could say that it is an exponential time algorithm, right? Or it is a problem whose solution requires some exponential time complexity. Okay. So here, because of that reason, I would say that this CNF satisfiability problem is NP hard. Okay. So to prove other problems are also NP hard, what I have to do here is I have to consider this as a base problem. Okay. So CNF is a base problem that we can use to prove the problem is NP hard. To prove another problem is NP hard, right? So here we have seen that why we are considering it as a NP hat because it is having some exponential time complexity. So here I have taken one combination like x1 is equal to 1, x2 is equal to 0, x3 is equal to 1. So by substituting these values in the satisfiability equation, I am getting the answer as 0, that is false. So this combination is not giving the exact result. So that's why I have selected the another combination as x1 is equal to 1, x2 is equal to 0, x3 is equal to 0. So by substituting these values in the given satisfiability equation, I got the true result, right? So since I got the true result, the solution for this problem, the one of the solutions for this problem is 1 comma 0 comma 0. So that means x1 is equal to 1, x2 is equal to 0, x3 is equal to 0. So this is the solution for this satisfiability problem. Now we can relate any NP problem to CNF satisfiability problem, right? So in order to solve any NP class problems or NP hard problems, what we can do here is that we can relate this problem with the another NP hard problem, right? So whenever we relate one NP problem with the another NP hard problem, we call this property as reducibility. Okay, so this reducibility property is applied to solve the NP hard problems. Okay, so in if CNF satisfiability problem is solvable in polynomial time, then another NP problem can also be solved in the polynomial time. So what we are doing here is we are establishing the relationship between NP hard problems, and we are saying that if one particular problem is solved, then another problem can also be solved. Okay, so let me consider here. I am having a problem A and problem B. If I could able to reduce a problem A to problem B, if I get a solution for problem B, then definitely I will also get a solution for problem A. Okay, so this is how we are establishing the relationship between the NP hard problems, and we are solving them. Okay, so let me explain with one example here. So here I am using the concept of reduction. Here I have taken the satisfiability problem. So as I explained that satisfiability problem is considered as NP hard problem, let me say, and the click problem is something like harder problem, right? So what I could do here is I can reduce this satisfiability problem to click problem. Okay, so if the click problem is solvable in a polynomial time, then satisfiability problem could also be solvable in a polynomial time. Okay, so here one more point I would like to say here is, if satisfiability is NP hard problem, if satisfiability is reduced to some other NP hard problem, then both problems will be considered as NP hard, right? So if satisfiability is reducible to click problem, then click problem will also be considered as NP hard. Okay, so if satisfiability is NP hard and it is reducible to click problem, then click problem is also become a NP hard. Okay, if satisfiability is NP complete and it is reducible to some click problem, then click problem will also consider as NP complete. Oh, so that is the relationship that we can establish between the NP hard problems by using the concept of reduction. Okay, see here I have mentioned that point. SAT is reduced to click problem. If click problem is solvable in polynomial time, then SAT can also be solved in a polynomial time. Okay, so this is how we can relate the problems which are there in the NP hard category. So consider, if satisfiability problem is NP hard, then reducing the satisfiability problem to the click problem, then click problem will also become NP hard. Okay, so reduction is having the transitive property. Okay, so if one problem is solved, then another problem will also get solved. Okay, now consider that the satisfiability problem is having a non-deterministic polynomial time algorithm. So it will become NP complete. So just now I mentioned that if you are having a NP hard problem, if for that particular problem, if we can able to define a non-deterministic polynomial time algorithm, then that NP hard problem will become the NP complete. That means it will falls in the category of NP complete. Okay, so satisfiability is considered as a base problem that is used for proving that other problems are also NP hard, or it is also considered as a base problem to prove that the NP problems are NP complete problem. So this is the base problem. So remember this problem. Satisfiability is known NP complete problem. So it is already proved that the satisfiability problem is NP complete problem. Okay, so we can use this NP complete problem to reduce it to other problems. Okay, so see here, if satisfiability is reduced to L, if we are considering that satisfiability is NP hard, if it is reduced to L, then L will also become NP hard. Okay, and if we could say that if L problem is having a non-deterministic polynomial time algorithm, okay, then satisfiability problem will also become a NP complete. Okay, since L is having a non-deterministic polynomial time algorithm, so L becomes NP complete. Since L is NP complete, the satisfiability will also become NP complete, right? So this is the diagram. So in the previous session, we have seen that P is a subset of NP. So we are adding the concept of NP complete and NP hard to the previous diagram. So this is the how the diagram will look like. So NP is a one class. Okay, so NP hard is another class. Okay, So in this NP hard, we are having some intersection portion in which we get a NP complete problem. Okay. So already we have seen the definition. NP complete means the problem which is belongs to NP as well as NP hard. So that intersection region of NP and NP hard is considered as NP complete. Okay. So and moreover, the NP hard problem uh, may be NP class, may belongs to NP class. Okay. Next one. So next we are having one more problem that is called as click decision problem. So before going to explain this reduction concept by taking this click decision problem, so let me first tell you what is this click decision problem. So generally we are going to prove that click decision problem is NP hard, right? So how do we prove? We will see, but before that let me explain what is click. Okay. So here generally a graph is given. So in that graph what we have to do here is we have to consider the subgraph from the given graph. If the subgraph that we have taken from the given graph is complete, then it is called a click. Okay. So here you could see the figure A is a complete graph of four vertices, right? So if you consider the subgraph of the given graph, okay, if the subgraph is a complete graph, then you could say it is a click. Okay. So let me consider the subgraph is having the nodes 1 2. Okay. So if all the nodes in the subgraph are connected, then it is going to be considered as a click. So I am taking the subgraph as 1 2. So I am having the vertices as 1 2. So 1 2 nodes are connected to each other. So I could say that this graph is having a click. Okay. Next, see the second diagram. In this, we are having a graph, and I have taken the subgraph consisting of four vertices 1, 2, 3, 4. So all these four vertices are connected to each other, and they are forming a complete graph. So we can say that this graph is a having a click. So this graph is having a click. So you could also determine the size of the click based upon the number of vertices. So how many vertices are there in a click? So four vertices. So we could say that the size of this graph is the click of this graph is having size 4. Okay. Now next one, generally we have the problem like decision problem and optimization problem. So here we are considering click decision problem. So I think you should be in a position to identify the difference between decision problem and optimization problem. So what is decision problem? It is a problem for which the answer could be either yes or no, right? So one example is like, does the given graph G has a click of size 2? Yes, so the answer could be either yes or no. So you should verify the given graph, and if you could able to identify the click of size 2, the answer for this question will be yes. Okay, otherwise no. So such problems will comes under the decision problem. Next one, optimization problem. Find the maximum size click from a given graph G is called as optimization problem. So what we have to do, we have to consider a given graph, we have to identify the available clicks in a graph, and out of the available clicks we have to find out the maximum click. So that finding of maximum click of a given graph is considered as an optimization problem. Okay. Now, so here the objective is to prove that click decision problem is NP hard. So how do we prove this? So to prove this click decision problem is NP hard, what we have to do here is we have to consider the base problem which is already proved that it is NP hard. Okay. So which problem is already proved as NP hard? So already I mentioned satisfiability problem is already well known NP hard problem. So we could use that particular problem to prove that click decision problem is also NP hard. Okay. Uh, so see here, consider L1 and L2 are two problems. To prove L2 as NP hard, consider well-known NP hard problem as L1 and reduce L1 to L2. Okay, so already I mentioned that we have to consider L1 as a well-known NP hard problem, and we have to reduce that L1 to L2. If L2 is solved, then L1 will also get solved. Okay, so same property here we are applying for this. So satisfiability problem is well-known NP hard problem. So we are reducing that satisfiability NP hard problem to click decision problem. Okay. So if click decision problem is solved, then definitely satisfiability problem will also get solved. And we could say both the problems are NP hard. So let us have a look on this solution. So consider the satisfiability problem here. So already we know that we have to find out the values of x1, x2, x3 such that the satisfiability equation will get a true value. Okay, I have taken the satisfiability equation as like x1 or x2 and with x1 bar or x2 bar and with x1 or x3. So this is the constraint that I have taken. So I have to find out the values of x1, x2, x3 such that the result of this equation will get true. Okay, will become true. So the above formula is having three classes. So if we consider, we are having three classes. Okay, so class 1, class 2 and class 3. Okay, now what we are doing here is we are reducing this satisfiability problem to the click decision problem, right? So first step, we have identified the clauses in the CNF satisfiability problem. So we are having three clauses. Next, now what we will do, we will convert this satisfiability equation into the graph. Okay, so to find out the click, what is the thing that we require? We require graph. So here we are considering this satisfiability equation and we are converting it into graph. So in order to convert it into graph, we have to identify the classes here. So the number of classes are 3, C1, C2, C3. Now we have to generate the graph from these clauses. Okay, so I have taken the class 1 C1. In that, what are the boolean variables I am having? X1 and x2. So I am converting each variable as a vertex. So the variable is x1, so I am considering it as a vertex x1. Next, x2 is a variable, a boolean variable. I am considering it as another vertex x in class 1. Okay, same, the class 2 is having two vertices, x1 bar and x2 bar. Why? Because class 2 is having two boolean variables, x1 bar, x2 bar. So I am converting this x1 bar, x2 bar into vertices into the graph. So x1 bar is one vertex, x2 bar is another vertex. Next, class 3, x1 is one variable, x3 is another variable. So I am converting x1 as one variable and x3 as another, x1 as one vertex and x3 as another vertex in class 3. So now we have uh, got this vertices. Okay, now we have to connect these vertices such that we will get a graph, right? So there is a rule for connecting the vertices. The each vertex in each class must be connected to other vertex of every class. Okay, so here one constraint is that you cannot connect one vertex in class with its negation in another class. Okay, so that is the rule. Okay, so let me repeat the rules once again. The first rule is that every vertex in each class must be connected to every other vertex in every class. Okay, next one, you cannot connect the vertex in one class with its negation in another class. That means you cannot connect x1 vertex with its negation x1 bar in another class. So x1, x1 bar should not be connected. Okay. However, you can connect x2 and x1 bar. Okay. Now, so by applying this, we can able to draw the edges, okay, among the vertices of the clauses. Okay. Now, so this is the uh, connected graph that I got, right? So here, after connecting the vertices of all the clauses together by edges, we got this graph, right? And from this graph, we have to identify the click. Okay. So here I have taken one click which is having size 3. Okay, so I have taken the click of size 3. So in this the vertices are x1 bar, that is from class 2, is connected to x2 vertex of class 1, and they are connected with the vertex x3 of class 3. So this is how the vertices x1 bar, x2 and x3 are connected together. So it is a click of size 3. Okay, so here what we have done, we have converted this, reduced the CNF satisfiability problem into click decision problem. Okay, and we solved this click decision problem, uh, and the values that we got here is, that means the vertices that we got here is x2, x1 bar, x3, right? So if we substitute the solution of clicks problem in CNF, the CNF problem will also get solved. Okay, so let me substitute the result of this click problem into the satisfiability problem so that you will get a result for satisfiability problem too. Okay, so here what are the vertices? X1 bar. So x1 bar is a vertex in a click, so I am considering the value of x1 bar as 1. Okay, next another vertex is x2. So this x2 vertex we have considered in a click, so I am considering this x2 value as 1. Okay, and next another vertex that we have considered is x3 in a click, so x3 value is considered as 1. So totally we got three vertices, and we are considering those values as trues. Okay, so x2 is 1, that is true, x1 bar is also 1, it is true, and x3 is equal to 1, it is true. So substitute these values in the CNF satisfiability equation. Okay, so if you substitute these values into the CNF satisfiability equation, you will get a true result. Okay, so here we could able to prove that the solution of click decision problem will also gives the solution for CNF problem. Okay, so here we have seen that, so here we proved that the solution of the click decision problem can be used for solving the constraint satisfiability problem. Okay, CNF satisfiability problem. So based on this, we proved that click decision problem is NP hard. So to prove that click decision problem is NP hard, what we have done here is we have taken the base NP hard problem, that is already known NP hard problem. So that is satisfiability problem, and then we reduce this satisfiability problem to the click decision problem, and we solved the click decision problem. Okay, and we proved that the click decision problem is NP hard. Why? Because the satisfiability problem is NP hard. Okay, so since the satisfiability problem is NP hard, the click decision problem will also become NP hard. Why? Because the satisfiability problem has reduced to click decision problem. Okay, and last concept in this subject is Cook's theorem. So generally, this Cook theorem is used to prove that the satisfiability problem is NP complete. So generally, the Cook has proved that the satisfiability problem is NP complete. Okay, and moreover, he mentioned that any NP problem can be converted to satisfiability problem in a polynomial time. Right. So one point in reduction is that while performing the reduction, that means when reducing one problem into another problem, that reduction must be done in a polynomial time. Okay, so if that reduction is taking exponential time, then it is of no use, right? So the performing the reduction, while performing the reduction, ensure that that reduction will take the polynomial time. That means that reduction must be done in a polynomial time. So here the Cook mentioned that any NP problem can be converted to satisfiability problem in a polynomial time. We have seen this, right? So we reduce this NP hard problem, that is satisfiability problem, into the click problem. Okay, and that reduction has done in a polynomial time. Okay, In order to prove this, we require a uniform way of representing NP problems. Of course, so to perform that reduction, you should able to establish the relationship between the problems. So there must be a uniform way of representing the problem. See, in the CNF problem, what we have done, we have taken a satisfiability equation. Okay, then we have converted that satisfiability equation into the graph. Okay, and we have find the click in a graph. Okay, the solution of the click we can able to substitute in a CNF equation, and we could able to get a result for it, right? So we have to relate the problems in a uniform way. Okay, Cook theorem implies that any NP problem is at most polynomially harder than satisfiability problem. Okay, this means that if we find a way of solving satisfiability problem in a polynomial time, we will then be in a position to solve any problem in a polynomial time. Of course. So as we are establishing the relationship between the uh, problems, NP problems. So if we solve one particular problem, we will get a solution for another problem. Okay. In order to prove that an NP problem is NP complete, all that is needed is to show that SAT can be converted into it in a polynomial time. Okay. So SAT is a well-known NP complete problem because there exists a non-deterministic polynomial time algorithm for this satisfiability. Okay, and moreover, Cook also proved that this satisfiability problem is NP complete. Okay, so you may get a short answer question on this Quick's theorem. So just try to understand these points. So you must write these points in the examination. Okay. So this is about the computability. So this is the end of the unit 5. Okay, for R19 regulation, and unit 6, end of unit 6 for R16 regulation students. Okay. So this is the end of this unit 5. So here in this we discussed about the computation, what is computation problem, how those computational problems are divided into P, NP, NP hard, NP complete. Okay, and we have seen how to prove a particular problem as NP hard, and how we can prove a problem is NP complete. Okay, so mostly to prove any of the problem as a NP hard, we have to take the base problem that is CNF satisfiability problem. We have to convert that CNF satisfiability problem into the another problem. Okay, so if you solve this another problem, you could get a solution for this CNF also. Okay, so we are relating those problems. Okay. So that's it in this session. So in the next session, we will try to revise the concept. We will have the discussion related to the problem solving techniques, or the various queries that you are having in the problem solving techniques. Okay, that we will discuss in the next session. So that's it for today's session. Thank you for attending this session. If you get any difficulties, just try to get in touch with me. I will try to explain all your doubts in the next session. Okay, so that's it. Thank you for attending this session.